You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Scaling laws are one of the most influential discoveries in modern artificial intelligence, and they serve as a compass for understanding how far we can push the boundaries of model performance by making things bigger. At their core, scaling laws are empirical observations, patterns that researchers have documented when increasing the size of a model, the amount of training data, and the compute resources dedicated to training. These laws show that performance improvements are not random, but follow predictable mathematical curves. For example, as we expand the number of parameters in a model, we tend to see steady reductions in error rates up to certain limits. Similarly, when we increase the size of training datasets, models learn to generalize more effectively. The key is that these gains follow repeatable trajectories, which means researchers and organizations can plan ahead, budgeting resources and predicting the returns on scaling before committing to enormous training runs. The historical emergence of scaling laws did not happen overnight. In the early days of machine learning, progress was often seen as incremental and task-specific, with no clear rule that larger models would necessarily be better. But around the late 2010s, as deep learning architectures like transformers became more common, researchers began noticing striking regularities. Papers published by teams at OpenAI and other labs demonstrated that when models were trained with steadily increasing amounts of data and parameters, their performance on benchmarks improved in highly predictable ways. This was not merely a lucky trend, but an indication that scaling laws reflected underlying dynamics of learning in neural networks. Just as physicists look for consistent patterns in nature to understand laws of motion, AI researchers saw scaling curves as a way to map the landscape of intelligence itself. The recognition that growth followed consistent patterns fundamentally reshaped strategies for research and investment. To appreciate scaling, one must understand parameters and model size. Parameters are the tunable weights inside a neural network, the numbers that adjust during training to capture patterns in data. In small models, you might find millions of these weights. In today's largest systems, there are billions or even trillions. Each parameter is like a knob on a control panel, tuned to represent some feature or association. The more parameters you have, the more complex patterns the model can store. But parameters are not magical by themselves. They need to be paired with high-quality data and sufficient compute. Nevertheless, the raw number of parameters often serves as a shorthand for a model's potential capacity, much like the number of transistors once symbolized the power of computer chips. When researchers speak of larger models, they are usually referring to the explosion in parameter counts, which has been one of the most visible markers of AI progress. Yet scaling is not just about model size. Dataset size plays an equally vital role in shaping outcomes. A model with billions of parameters trained on a tiny, narrow dataset will overfit, memorizing quirks rather than learning general patterns. Scaling laws demonstrate that meaningful gains come from pairing large models with large, diverse datasets. The analogy here is straightforward. Imagine teaching a student with an encyclopedic memory but only giving them a few newspaper clippings to study. Their memory capacity would be wasted. In contrast, feeding that same student a wide-ranging library allows them to put their memory to use and develop nuanced understanding. In AI, dataset scaling means broadening the range of contexts the model has seen, which in turn makes its outputs more reliable across different tasks. Thus, model size and data size scale together in a kind of partnership, each amplifying the other. A third dimension of scaling is compute, the raw processing power needed to train these enormous systems. Larger models require exponentially more floating-point operations to adjust their parameters during training, and larger datasets mean more passes through that data. Compute becomes the enabler and also the bottleneck. Researchers quickly discovered that without massive parallelization, specialized hardware like GPUs and TPUs, and optimized training pipelines, scaling would grind to a halt. It is not just about having more computers, but orchestrating them efficiently to spread workloads. In this sense, compute is like the fuel for a rocket. The bigger the rocket, the more fuel required. But fuel costs money, and the logistics of handling it become increasingly complex. This third dimension makes scaling a challenge not only of science, but also of engineering, logistics, and finance. The relationship uncovered through scaling is often expressed as a power law. As models grow larger in parameters and data, their performance improves in a smooth, predictable curve of diminishing error. This discovery was revolutionary because it allowed researchers to plot where they were on the curve and extrapolate where they could go with more resources. It is akin to mapping out a mountain climb. Knowing that each step forward will predictably increase elevation gives climbers confidence in how much further they can ascend. However, the curve does not extend forever. It bends as diminishing returns set in. Nevertheless, within practical ranges, the power law pattern gives scaling its predictive power and explains why so many organizations now treat model growth as a systematic path rather than a gamble. Importantly, these scaling laws have been observed across multiple domains. While they were first documented in large language models, researchers have found similar patterns in vision systems, reinforcement learning tasks, and even multimodal architectures. Whether the model is processing words, pixels, or a combination of sensory inputs, scaling seems to follow the same rules. This cross-domain generality suggests that scaling laws are not accidental quirks of one field, but fundamental properties of deep learning. Such universality gives them additional weight, convincing many researchers that scaling is not just a temporary strategy, but a foundational principle of how machine learning systems improve. Yet scaling comes with costs, not just financial, but also environmental and social. Training trillion-parameter models requires enormous amounts of electricity, specialized hardware, and months of runtime on vast clusters of machines. These costs translate into millions of dollars per training run, making such experiments accessible only to a handful of wealthy organizations. Beyond money, the energy use contributes to carbon emissions, raising concerns about sustainability. In this sense, scaling reflects not only scientific ambition, but also societal trade-offs. Just as industrial revolutions reshaped economies while introducing pollution, the scaling revolution in AI drives progress while raising questions about environmental impact. Recognizing these costs is essential for honest conversations about the benefits and limits of scaling. Moreover, scaling exhibits diminishing returns. The first leaps in model size produce dramatic performance improvements, but each subsequent doubling or tripling of parameters yields smaller relative gains. This pattern is intuitive when compared to human learning. The first few hours of practice in a new skill often bring rapid progress, while additional practice yields finer, less dramatic improvements. Scaling models follows the same arc. The diminishing returns do not mean scaling is futile, but they do remind us that growth cannot continue indefinitely as the primary driver of progress. At some point, efficiency, architecture, and alignment matter more than raw size. This realization tempers the enthusiasm around scaling and encourages balanced strategies. A fascinating feature of scaling is the presence of threshold effects, where certain capabilities emerge only once models surpass specific sizes. Researchers noticed, for instance, that small models cannot perform in-context learning, the ability to generalize from a few examples presented during inference, but larger models suddenly display this skill. These emergent behaviors seem to appear abruptly, much like water boiling once it reaches a certain temperature. Threshold effects suggest that scaling is not only about quantitative improvements, but also about crossing into qualitatively new territories of capability. This phenomenon fuels much of the excitement about scaling, as it hints that hidden abilities may await at higher levels of size and complexity. Scaling has also played a major role in benchmark performance. Many of the breakthroughs reported in natural language understanding or vision benchmarks are directly tied to scaled-up models, sometimes paired with clever training tweaks. Scaling has thus become a strategy for achieving state-of-the-art results across tasks, often serving as the differentiator between ordinary models and headline-grabbing systems. Critics argue that this reliance on scaling makes progress appear more dramatic than it truly is, since it depends on throwing resources at the problem rather than innovating fundamentally. Still, the linkage between scaling and benchmark dominance cannot be denied, and it explains why scaling remains at the center of research and competition. The industry race to scale reflects these dynamics vividly. Research labs and corporations compete to build ever larger models, not only for academic prestige but also for market positioning. Bigger models are often seen as more capable, more appealing to customers, and more likely to attract talent. This race has become a defining feature of the AI landscape, with organizations pouring resources into scaling efforts even as they acknowledge the costs. The parallels to the space race are striking. Nations once competed to build the largest rockets, while today organizations compete to train the largest models. Both endeavors combine ambition, rivalry, and the pursuit of new frontiers. Still, scaling alone is not enough. A large model trained poorly, deployed carelessly, or aligned weakly with human goals can cause harm despite its size. Efficiency techniques, careful evaluation, and strong safety frameworks are needed to complement scaling. Without them, scaling risks producing bloated systems that consume vast resources without delivering proportionate value. This recognition has led many in the field to emphasize that scaling is powerful but not sufficient. It is a foundation on which other improvements must be layered. Finally, scaling carries ethical and equity implications. Because only a few organizations can afford the massive resources required, the benefits of scaling are concentrated in their hands. Smaller labs, startups, and academic groups struggle to participate at the frontier. This concentration raises questions about access, fairness, and the direction of AI development. Will knowledge and power in AI be monopolized, or will strategies emerge to democratize access to scaled systems? These are not merely technical questions but societal ones, reminding us that scaling exists within broader contexts of equity and justice. Even at large scales, reliability remains imperfect. Larger models may reduce average errors, but they do not eliminate problems like hallucinations, biases, or ethical risks. In some cases, scaling may even amplify issues by making outputs more persuasive while still flawed. This highlights the duality of scaling. It improves performance in measurable ways, but cannot substitute for alignment, safety, or governance. In other words, bigger can be better, but bigger is not automatically wiser. The challenge is to pair scaling with strategies that make systems trustworthy, not merely powerful. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Scaling laws are not only descriptive, but also prescriptive. They act as a research compass, guiding decisions about how large to build the next generation of models and how much compute and data will be necessary. Instead of training blindly and hoping for improvement, researchers can look at scaling curves and predict, with surprising accuracy, what performance to expect if they invest in a model twice or 10 times as large. This predictive guidance reduces risk in resource allocation and provides justification for massive budgets. For organizations with limited funds, scaling laws also serve as a reality check. They can show that a modest increase in parameters may not yield enough improvement to justify the cost. In this sense, scaling laws help both the ambitious and the cautious, offering a roadmap that aligns research planning with predictable outcomes, much like civil engineers use load-bearing calculations before constructing a bridge. The predictive value of scaling curves cannot be overstated. By charting performance across different sizes of models and datasets, researchers generate scaling equations that allow them to extrapolate future improvements. If a language model of 1 billion parameters performs at a certain level, and a 10 billion parameter model improves along a consistent curve, then projections for a 100 billion parameter model can be made even before training begins. This is akin to Moore's law in computing, where transistor counts doubled predictably over decades, giving the industry a sense of direction. Scaling curves allow AI research to follow a similar path, where investments and expectations can be aligned with empirical evidence rather than speculation. This predictive capability has reshaped how labs, companies, and governments plan their AI strategies, reducing uncertainty in a field once seen as unpredictable. Within scaling, an essential consideration is the trade-off between data and parameters. A huge model trained on a small dataset will waste its potential, while an enormous dataset paired with a tiny model will not be fully leveraged. The optimal path lies in balance, increasing both parameters and data in proportion to one another. Researchers have discovered that when this balance is maintained, scaling curves remain smooth and predictable. But when the balance tilts too far in one direction, performance stagnates. The analogy is to farming. A field with rich soil but too few seeds will underperform, while too many seeds planted in poor soil will struggle to grow. Just as successful agriculture requires both fertile ground and sufficient planting, successful AI scaling requires harmony between data and parameters, ensuring that capacity and information rise together. Because of the immense costs of scaling, researchers have explored compute-efficient approaches that capture many of the benefits without requiring exponential resources. Techniques like sparsity, where only a fraction of the model's parameters are activated for each task, reduce computational load while retaining scale benefits. Knowledge distillation allows smaller models to learn from the outputs of larger ones, creating compact yet powerful systems. Parameter-efficient tuning methods, such as adapters or low-rank factorization, allow models to be specialized without retraining their full parameter set. These innovations are like finding fuel-efficient engines for large vehicles. They preserve performance while reducing energy and cost burdens. In practice, compute-efficient approaches are not just technical tricks, but essential strategies for broadening access, enabling more organizations to participate in scaling without billion-dollar budgets. The environmental considerations of scaling loom large in public debates. Training trillion-parameter models consumes vast amounts of energy, often equivalent to the electricity usage of small cities over the training period. This consumption translates into significant carbon emissions unless offset by renewable energy sources. Critics argue that unchecked scaling risks creating an environmentally unsustainable trajectory for AI progress, where performance improvements come at the expense of climate goals. Proponents counter that AI itself can contribute to energy optimization and climate solutions, but this does not erase the immediate footprint of large-scale training. These concerns force the field to confront hard questions. Should scaling be pursued at any cost, or should efficiency and sustainability be weighted alongside raw performance? The answers will shape both the ethics and the practical direction of the scaling frontier. Even beyond environmental and financial limits, scaling faces practical ceilings in hardware and latency. As models grow, they require larger clusters of GPUs or TPUs, more memory, and more sophisticated interconnects. At some point, bottlenecks in hardware design and data transfer slow progress. Latency also becomes an issue. Even if a trillion-parameter model can be trained, serving it quickly enough for real-time applications may prove challenging. These practical limits remind us that scaling is not infinite, but bounded by the physics of computation and the economics of hardware. This recognition drives interest in complementary innovations, such as model compression, hybrid approaches, and specialized architectures that deliver performance without requiring unlimited scaling. One of the most intriguing aspects of scaling is the appearance of emergent behaviors. Researchers have observed that certain capabilities, like in-context learning or advanced reasoning, do not exist in smaller models, but suddenly appear once models surpass a critical size. These emergent skills are not explicitly programmed, but arise spontaneously from scale. The phenomenon is similar to how the collective behavior of ants produces complex colony structures, even though each ant follows simple rules. In AI, emergent behaviors suggest that scaling unlocks qualitatively new dimensions of intelligence. While exciting, these behaviors also raise concerns. since they may bring unexpected side effects or risks. Understanding and harnessing emergence has become one of the most active areas of research, illustrating that scaling is not just about quantitative improvement, but also about crossing thresholds into qualitatively new capabilities. Scaling generally improves robustness, as larger models tend to generalize better across tasks and domains. By training on more data and incorporating more parameters, they capture broader patterns and reduce overfitting to narrow contexts. This means that, on average, scaled models produce more reliable outputs. However, scaling also has a darker side. It can amplify hidden biases or systemic errors embedded in the data. If a bias is present in the training set, a larger model may reproduce it more forcefully and persuasively. Thus, scaling can make models both more powerful and more problematic at once. The challenge lies in ensuring that robustness does not come at the cost of fairness or ethical soundness. This duality reminds us that scaling is not a simple win-win proposition, but a complex balancing act. Another concern tied to scaling is global resource inequity. The cost of training massive models limits participation to a handful of corporations and well-funded labs. Academic institutions, smaller companies, and researchers in developing regions often lack the hardware, electricity, or funding to compete. This concentration of capability raises serious questions about equity in AI research. Will knowledge and power be monopolized by a few, or will collaborative frameworks emerge to share access? Without intentional efforts to democratize scaling benefits, we risk creating a world where AI capabilities are as unevenly distributed as wealth, deepening divides rather than narrowing them. Recognizing this inequity is a first step toward developing more inclusive research practices, policies, and collaborations. Given the constraints and inequities, researchers are exploring alternative frontiers beyond pure scaling. Innovations in architecture, such as attention mechanisms, memory-augmented models, and multimodal designs, offer performance gains without always requiring exponential growth in size. Fine-tuning strategies allow smaller, specialized models to achieve near state-of-the-art results on targeted tasks. Hybrid systems combine symbolic reasoning with neural learning, blending strengths from different traditions. These alternative approaches suggest that the future of AI will not rely on scaling alone, but on a mixture of growth, efficiency, and creativity in design. By diversifying strategies, the field can continue advancing even when raw scaling encounters walls. The dynamics of scaling also differ between open research communities and proprietary corporate labs. In open settings, researchers share scaling experiments, publish data on curves, and collaborate across institutions. This transparency accelerates collective understanding but often operates at smaller scales. In contrast, corporate labs with vast resources may keep scaling results secret, protecting competitive advantage. The tension between openness and secrecy creates asymmetries in knowledge and innovation. While open communities push forward foundational understanding, corporations often dominate the bleeding edge of scale. This divide shapes the global landscape of AI research and raises questions about how knowledge should be shared or protected in a field with such profound societal impact. For organizations planning their AI strategies, scaling laws play a central role in resource allocation. Decisions about whether to train larger models, invest in hardware, or focus on fine-tuning are often informed by scaling curves. Executives and technical leaders use these insights to plan budgets, predict returns, and manage risk. In practice, scaling laws become a strategic tool, not just a scientific observation. They enable organizations to map the trade-offs between cost and capability, guiding choices that affect competitiveness and innovation. In this way, scaling laws sit at the intersection of research, engineering, and business strategy. Deploying scaled models into products introduces further complexities. Even if a large model performs exceptionally in research environments, real-world deployment requires engineering trade-offs. Running a trillion-parameter model on consumer devices, for instance, is impractical without compression, distillation, or server-based inference. Developers must weigh performance against latency, cost, and accessibility. The challenge is to translate the promise of scaling into usable products, ensuring that the benefits reach end users without prohibitive costs. This deployment phase often reveals gaps between theoretical scaling and practical usability, making it one of the most critical arenas for innovation. As we close this episode, it is worth noting the bridge to our next topic: tokenization. Scaling laws describe how bigger models and datasets yield improvements, but these gains depend on how text and other inputs are represented in the first place. Tokenization is the process by which models break down language into units they can understand, and it interacts deeply with scaling. Larger models are more powerful, but if tokenization is inefficient, much of that power is wasted. Thus, understanding scaling naturally leads us to examine the mechanics of input representation, which will be the focus of our next discussion. In conclusion, scaling laws explain why bigger models, datasets, and compute resources produce predictable improvements in AI performance. They serve as a compass for research and strategy, offering predictive curves that guide decisions about investments and expectations. Yet scaling also comes with costs: financial, environmental, and ethical, and faces limits in hardware, equity, and practicality. Emergent behaviors, robustness gains, and amplified biases remind us that scaling is both powerful and complex. Complementary strategies, from efficient training to architectural innovation, highlight that scaling is not the only path forward. As the industry balances ambition with responsibility, scaling laws remain one of the most important tools for understanding what bigger really buys us, and where we must look beyond size for the next breakthroughs. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.